Hi everyone, my name is Guowen Xie, and today my topic is acid and base. First, let's see the definition of acid and base. When we talk about acids and bases, we are often referring the Bronsted-Lowry definition. According to this model, acid is something that donates a proton, and base is to accept a proton. And the way that we use to measure the value of acid and base is pH. We can see the pH scale on the right. 0 to 7 indicates acidity, and 7 to 14 indicates base. And the pOH is a measure of hydroxide ion concentration. We can calculate it by using 14 minus pH value. Because of acidity, it will have different results when it reacts with water. For example, when strong acid or base reacts with water, we can see that it completely ionizes, that every molecule of acid will transfer its acidic proton to a water molecule. Every molecule reacts to completion. But when weak acid or base reacts, they can only partially ionize, and they establish an equilibrium between the ionized and the unionized form. So, we can say there are conjugate bases and conjugate acids. In the Bronsted-Lowry definition of acids and bases, conjugate acid-base pairs consist of two substances that differ only by the presence of proton. A conjugate acid is formed when a proton is added to a base, and a conjugate base is formed when a proton is removed from an acid. At most of the time, you can use an indicator to monitor the color changing to see the different pH value. There is an example of the reaction between HPH and water. According to the concentration of hydronium ion, the color will be influenced. So, if there is more hydronium ion, the system will respond to use up some of hydronium, removing some of pH minus, and making more HPH. So, the color will be the HPH form. But if there is less hydronium ion, the system will respond to make more hydronium ions, and removing some HPH, and making more pH minus. So, the color will be the pH minus form. According to the features of acids and bases, it can be used in the technology, such as the different kind of batteries. So let's see the details of lead-acid batteries. Despite having a very low energy to weight ratio and a low energy to volume ratio, its ability to supply high surge currents means that the cells have a relatively large power to weight ratio. In the discharged state, both the positive and negative plates become lead sulfate, and the electrolyte loses much of its dissolved sulfuric acid and becomes primarily water. A buffer is a solution that has the ability to resist changes in pH when limited amounts of acid or base are added to it. Buffers are made by combining weak acid or base with its conjugate. In such a solution, because both the acid and the conjugate base are present, they are able to neutralize small amounts of any acid or base that are added to the solution. Many logical fluids are buffer solutions because they maintain a steady pH to avoid loss of critical biological function, such as the bloodstream. Buffer solutions of a particular pH can be prepared using a Hansen-Hasselbalch equation, as shown on the slide. We know about pH and pKa is similar in that if pH is negative log of the hydronium concentration, pKa is a negative log of the Ka for that acid. Let's see an example. In an acidic solution with a pH of 3.4, 78% of the acid is ionized. So what is the pK of the acid? First, we can write the equation. And we can input the numbers into the equation. So it would be the 3.4 is equal to pKa plus 0.55, and the answer is 2.85. In the natural world, there are different kinds of buffer system, such as a phosphate buffer system, protein buffer system, and the minerals react with oxalic acid, and the limestone rock and acid reacted consumes or add hydrogen ions to the water, buffering the pH. We can talk about the limestone and acid rain reaction in details. There is a diagram that shows the process of the reaction on the right. So we can see the calcium carbonate react with hydrogen ion from the acid ring and producing the products which are calcium ion and bicarbonate ions. Then bicarbonate from the first equation reacts to the hydrogen and producing carbonic acid. And the buffer systems are very important in many areas. For example, in the physiological system, the buffer systems functioning in blood plasma include plasma proteins, phosphate, bicarbonate, and carbonic acid buffers. The kinases help control acid-base balance by excreting hydrogen ions and generating bicarbonate that helps maintain blood plasma pH within a normal range. And in pharmaceuticals industry, buffers are used to run biological assays. For example, enzyme activity varies with pH, so you have to keep the pH constant to get accurate results. Buffer solutions are used in medicines that require a constant pH. And last, buffering is also important in living systems as a means of maintaining a fairly constant internal environment. Small molecules such as bicarbonate and phosphate provide buffering capacity as to other substances.